Aarhus in Denmark. I had the pleasure of meeting one Christian Armateur, and if there's any electrochemists in the house, they will probably know who Christian Armateur is. He's a French electrochemist, very, very senior. Look him up. Anyway, he told me a couple of things. I had the pleasure of an evening with him, and also the following day of seeing a lecture of his. The first thing was about transition states. But I think the most interesting thing that I can pack into this minute and a bit that I've got left here, I'm not starting now, I'm just fitting in time. the thing that I can talk about right here, which is not in the presentation, but I think it's relevant, is he was talking about, he's a catalytic electrochemist specialist, and he was talking particularly about platinum catalysts in the process. And he was talking through this process, and there's one thing that came out of that whole hour presentation was that you go through the catalytic cycle and you've got this energy coming in and out during the course of doing the catalysis through the cycle. And to return the catalyst back to its original state, you can't do that by just applying heat. He said you need to apply some electricity or some light. And so having strontium-90 in there kicking out some electrons might assist in getting a catalyst back to its original position. Putting electricity through the wire might do that. Are we timed? Okay, all right, I just wanted to add that in there.
Now, let's start the afternoon session. The first speaker is MFMP GlowStick series. A high temperature experiment platform by Dr. Greenyer.
I'm not a doctor. Just Bob's fine. Okay, so my name is Bob. I am here representing an international community of researchers, some paid but mostly unpaid. In fact, pretty much all of us unpaid. But we have donors, and I want to thank those, and that's what makes this possible. I'm mostly representing other members of the group's research, and so if you'd like to go to the next slide. So I've got about 2 minutes to slide. So after the Ghana report, there was open questions about the emissivity calculations used to estimate the power. This is all in a CMNS paper which will be published or is published. It's going to be published very soon, so I'm just going to roughly run over it because we've not put this into public before. Essentially, we built a replica of the Ghana reactor. We've got it here if you want to have a look after. It's not the exact one we used. And we used a B-type, a Williamson-IR dual-band pyrometer, and a K-type in addition to the Optris camera, which was equivalent to the one used in the Ghana report. Williamson-IR pyrometer is the leading technology and the one that everyone in the hot industry will tell you need to use if you want to have any chance of getting the temperature of alumina right at elevated temperatures. So it's an $11,000 piece of equipment, and they let us borrow it for a couple of weeks for $1,100. And the B-type, the K-type, and the pyrometer agreed with the Optris. If we set the Optris to the value recommended in the Optris manual for emissivity of alumina. If you go to the next slide, please. So essentially, we did our homework, and we ended up with our temperature was this reported in Lugano, our temperature was this reported in Lugano, and the net result of this is that we effectively demonstrated that the COP in Lugano is actually more like 1.13 to 1.32, so very much more lower than the that reported by the Lugano report's authors. So we couldn't dismiss all of the excess heat, but you know, this is getting down to not very interesting levels. Okay, so we developed Alan Goldwater in California developed this GlowStick apparator, and we have an active and a control side. Active control. And we have alumina in one side and our active materials in the other. It's calibrated so that we have an external K-type thermocouple that doesn't go out of its operating range. And we have an internal thermocouple, and we produce a calibration curve for internal temperature as assessed by external temperature. And that gives us a good idea of what the temperature is in the cell. We monitor the pressure and can control hydrogen and vacuum through this T-junction here. Same gas pressure both sides, right side fuel, left side alumina powder. Calibrated, that's what I've said, and we monitored in GS 5.2 and other experiments with sodium iodide, and in other experiments with a range of other detectors, things like that. In the 1st to 2nd of February, we saw this spectrum coming out. Actually, we didn't know that was there. We were publishing our samples on a regular basis, our integration periods, and these were put into the public domain. At the end of the experiment on the 16th to the 17th of February, a crowd research identified this anomaly, which had occurred just as we were doing this. And what was that? This was the first time we went through sort of 900 to 1,000 internal temperature. We then sort of dropped down, and this was deliberate to try and create some precipitation of nickel nanoclusters in the lithium. And also we dropped the pressure there. The pressure's not on that graph, but all the information's available on our website. And then we kicked it back up again. And somewhere in this integration period 7, this occurred. So we don't exactly know how long it was for, but this occurred. And so, sorry, it says possible bremsstrahlung. It might be other type of beta-based radiation signal, but we don't know. More investigation is needed. So this is the experiment that we followed on GlowStick 5.3. So everything up to here is well documented in the CMNS paper that you'll be able to read soon. This is where it's not analysed, and I think my laser pointer died. No, there it is. What we added was, because we saw some sort of photon emission, we thought, hell, we better see if there's any neutrons coming out of this thing. So we had 2 types of neutron detector. One was for fast neutrons and one was for slow neutrons. This is our GlowStick reactor here, active side, passive side. Up here we've got our beryllium window, 3 to 100 and something kV X-ray detector. Down here we have Amtech 123 cadmium telluride detector. It's under this alumina felt. We've been told by the people at Aarhus University that this detector and this detector, because of its position and its sensitivity, would basically see nothing. So that was useful. There is a serious problem with this type of apparatus. It gets too high to be able to use these pieces of equipment effectively. So we need to solve that in order to be able to analyse what might be going on here or not going on. So we have a live webcam looking at these bubble detectors, and if you go to the next slide. Live on camera, we saw these bubbles appear. And we had never seen any prior to this point in time or after the experiment. And we were doing everything we needed to do to reset them on a regular basis. This is the fast neutron detector, this is the slow thermal neutron detector. The fast was kicking out about 2 average a day, it didn't matter whether the experiment was running or not. This did nothing, and then it did. And it was quite fun because we spotted one. And then I went to look at it and I called Skip over. I said, there's something going on, there's a bubble in here. And then right in front of my eyes, about that far away, another one appeared. And I thought, well, I better get a step away from the reactor. Anyway, this occurred between 305 and 315 degrees from the calibration curve on the inside of the reactor. Dennis Craven says the interesting thing about that temperature range is where the wave function of the deuterium matches the nickel lattice. Okay, I don't know how important that is, and maybe you guys can think about that a bit more. So, because we saw neutrons, we felt that we would step back from researching for a little while, and we found lots of other people starting to report neutrons. I think Clean Planet's Painton is saying they can reproduce neutrons based on the high voltage tension. So we thought it would be very important that all of the replicators and experimenters in the field that we were working with would have some sort of neutron detection. And it wasn't sufficient to use these bubble detectors, the solid angle, the sensitivity, and so forth. And neutron detectors are stupidly expensive for a crowd-funded project. So Bob Higgins, who's a bit of a whiz with these sort of things, he got some 3 helium detectors from the Soviet Union, some CHN-32s, and he built this open source neutron detector. You can, when you get this file, you'll be able to go there and it gives you an incredibly detailed document with all the circuits and everything. And if anyone in the room requires a neutron detector, we can supply them with boards, and unfortunately you have to make it up themselves, a bit fiddly, but I think everyone should have neutron detection. We're hoping to be able to characterize this apparatus soon because we want to use it in experiments, as I'll show you later on. Very cheap, and it uses this sort of, whatever it is, you can read that later, and it detects this background when it's sat next to a bunch of lead. Okay, so this is our tool set right now, and as I said before, the 300 to 100 keV and the CDTE would never have seen anything in GlowStick 5.3, and it's a bit of an intractable problem. So, next slide. Okay, so what we found is that we tried our very, very best to replicate our 5.2 experiment in 5.3. We did everything. The reactor was essentially the same, the processing was the same. There were a few blips where we forgot to turn the pressure up or down at the right time. And what this told us was we really need to be able to automate the process. Because you simply cannot ensure one experiment is exactly the same as the previous one unless we have some detailed automation. So as part of that process, Bob Higgins has designed an open source back pressure system so that if we have a pressure profile in an experiment, we can actually ensure that the pressure profile between an experiment that was apparently showing something interesting and the next run of that experiment would be exactly the same. So if we wanted to emulate the pressure profiles of Parkhomov, for instance, we could do that. And so we've designed that again. That's open for everyone to use. Brian Alston did try and replicate us. He's the most, as we are aware, he replicated us as much as possible, but he took on board the potential that there was energy coming out in the low energy photon range. And so he built a lead jacket around his ceramic reactor to capture anything, and it obviously became molten and so on, but he didn't really see any excess heat under that basis. But what he did do is around about 1,000 degrees, he depressurized the reactor down to vacuum. Is that already? Wow, okay. Depressurized the reactor and then put some fresh hydrogen in, and he got a spike, a bit like we saw with Chilani Wire in 2013 when he repressurized the cell. So that's interesting. It's kind of showing something similar to what maybe we've seen. And we're looking for automation, both Alan Goldwater and Matthew Villa. Next one. Okay, so yeah, that's the one I've just described. And next one. This is replication that was going to be running this week, but unfortunately David Daggett phoned in energy. This is the independent replication. As you can see, it's very, very similar. He's gone to extreme lengths, but he's tried to just improve the way the thermocouples attach based on our experience. So that should be running soon. This is more information about what it is, and you can see that from the presentation. Artis University, they've got significant tools. They're capable of adding robust testing. And I have established, whilst being there, what is holding back the Lena field as far as acceptance is going. And we have a responsibility as a community to work together to come up with the evidence that makes it very, very easy for people at capable institutions to be able to take part in this research process. I totally stand behind what the plenary speaker said. So we're going to do one experiment which is using 18 oxygen. There's a peak at 5.1, 5.2 for this PM reaction. We obtained some aluminium 18 oxygen from Russia, and we put that into the cells, and if Piantelli is right, it's kicking out 0 to 5.7 megaelectron volt protons. It'll do this PM reaction, and we should see, next slide, no, we should see the 511 keV positron electron annihilations, and we will be able to observe that with some of our apparatus further away from the cell. This will add support or take away support from Piantelli's theory. We've also acquired some 62 nickel because all of these people said 62 nickel is useful. You can look at that later. We're doing electric discharge, the thing I was talking about earlier, the fact that the catalyst gets reset with electricity, not heat or light. This could play into that. Note that Rossi has added to his patent 50 to 100 kV stimulation. The Canon patent from 1989 used something similar, clean plan, and everyone's using sort of electricity in some form to make this reaction apparently work better. Next slide. Okay. Future plans, so summary. 18 oxygen experiments, nickel 62 experiments, using lithium aluminium deuteride and the modified electromagnetic stimulation. And this is off a patent which has similar claims to the way the condensation of matter, the TSC theory of Akito Takahashi. And it's a 2006 patent which was published in 2007, a full 3 years before Rossi did his first public demonstration. Claims it works between 300 and 1500 degrees. It claims there's no radiation outside the reactor. It claims it can self-sustain. It claims it produces helium. It claims it produces 6 lithium. And so it's really interesting. I encourage you to go and look at this video, which we published last week. Okay, thank you very much to our donors. Thank you very much for listening. If there's any questions, I'll take them now.
Thank you very much. Is there a question or comments?
Yeah.
Yes.
That report you have up there about Violante's apparent detection, I believe you should go and check with Violante. I believe he withdrew that result.
He wants to review that result.
No, I believe he withdrew it.
He withdrew it, okay.
So check with Vittorio.
Well, the physicists at APAS seem to reject the paper as well, so it's not it's just a photon stimulation one. Anyone else? Yeah, I'll ask you that. Anyone else?
Yes.